In Standard 18, we will be talking about pH as it pertains to acids and bases. And so we've already talked about acids and bases a little bit before in the Bronsted-Lowry definition. There are three different definitions of acids and bases, and the definition that we've already seen was that in which, in especially neutralization reactions, an acid is considered anything that donates hydrogen ions easily, and whatever takes those ions is considered a base. So, for example, in this neutralization double replacement reaction, we take hydrochloric acid, a very strong acid that gives away hydrogen ions, and it gives those ions to sodium hydroxide, specifically the hydroxide, which serves as the base. And in these neutralization reactions, we have a sort of stabilization of the substances so that it becomes much easier to deal with. So we take a very strong acid and a very strong and dangerous base and turn it into water and salt. Okay? And in some cases where you're not dealing with a strong acid and strong base, you wind up with this sort of reversibility where you can take a base and turn it into an acid. Like in this case, NH4 plus ammonium can donate a hydrogen ion to hydroxide, a polyatomic ion, and turn that hydroxide into water and ammonium into ammonia, NH3. But this reaction is reversible in that the hydrogen can go back to the ammonia, which means that ammonium in this case was an acid, but it turns into a base because that reaction can go both forwards and backwards. But the other definition of acids and bases we're going to look at pertains to pH. It was pioneered by a man named Svante Arrhenius. He wrote, and he was an interesting guy, definitely a stereotypical genius. He wrote a 150-page paper that later won him the Nobel Prize at age 25. He also was so good at what he did that he served on the Nobel Prize committee. He was one of the people who determined who got Nobel Prizes and who didn't get Nobel Prizes for their work. And like all good scientists, he did have an arch nemesis, and his arch rival was Dmitri Mendeleev, who happened to be the guy who constructed the periodic table. Mendeleev was ridiculed for his ideas for a good chunk of his life and never actually won a Nobel Prize, largely because of Svante Arrhenius and their hatred for each other. Arrhenius also founded several fields, including immunochemistry, so the chemistry of our body's immune systems. And he also was a unique scientist in that he hopped between fields pretty quickly and easily. So after mastering chemistry, he decided to move on to other things. He studied biology, astronomy, you name a scientific field, he studied it for a while. But the big thing that we recognize him for now is his contributions for pH theory and the idea of acids and bases as he defined them. Now, the critical component of his theory is this reaction right down here, in which you have two water molecules. In any glass of water, in any sample of water, you can have this reaction occur where a hydrogen from one water molecule will be donated to another water molecule. Okay, so that hydrogen will migrate over to that other molecule, and you'll wind up with hydronium, which is H3O+, a polyatomic ion, and hydroxide, which is a polyatomic ion that we've already dealt with, okay, OH-. And this reaction can go back and forth and back and forth. Now, in any sample of water, this reaction occurs, and this is true. Okay, no glass of water is just pure water molecules, H2O. There will always be some hydronium and some hydroxide. Okay, but for the most part, it is mostly H2O molecules, and these hydronium and hydroxides in general tend to be in very, very low concentrations. And as long as those two molecules are in balance, hydronium and hydroxide, as long as you have the same amount of hydronium and hydroxide, then your pH is neutral and it's neither an acid or a base. And it's the balance between these two things that determines whether a solution dissolved in water is aqueous or is acidic or alkaline, also known as basic. So we can organize these scales onto the pH scale, and you've probably heard of the pH scale before, but what you may not have known is that the pH scale is just a measure of the balance between hydroxide and hydronium. Now, one disclaimer that I should share with you now is that a lot of circumstances you will see the hydrogen in hydronium just expressed as H+. So hydrogen ions, similar to the Bronsted-Lowry definition, are also another way of thinking about pH, which is where the term pH comes from. It's a measure of the hydrogen ion concentration. It's just that those hydrogen ions float around in hydronium, H3O+. Okay? So on the pH scale, a very low value is acidic. Okay, so a value of 0, which tends to be the lower domain of the pH scale, is going to be about as acidic as a solution can get, which means that that solution has a lot of hydrogen ions floating around in it and not very many hydroxide ions. On the other end of the pH scale, pH of 14, we have a very basic solution, or what we would call alkaline. Okay, two terms mean the same thing. And in an alkaline solution, we have a lot of hydroxide floating around, okay, a lot of those OH minuses, and not very much H+, or hydronium, depending on how you think about it. And so a pH of 7 would be what we consider neutral. And at a pH of 7, we have an equal amount of hydrogen and hydroxide. The two are in balance, which means it's neither acidic nor basic. So an acid, according to the Arrhenius definition, is anything that will increase the amount of hydrogen in a solution. And a base is anything that will increase the amount of hydroxide. And so to figure out what the pH of a solution is, we oftentimes use indicators. And indicators will change colors based on the pH of the solution. Okay, so there are several different indicators that we use in chemistry, and each indicator has its own sensitivity. So for example, bromophenol blue will change from yellow to blue at around a pH of 3 to 4. Okay, whereas phenolphthalein, if we were to look at that, changes from clear to pink at a pH of approximately somewhere between 8 and 10. So if you add phenolphthalein to a solution that is acidic with a pH of somewhere between 1 and 7, it will look clear. And as soon as it starts to turn alkaline, as soon as you put it in more alkaline solutions or more basic solutions, like for example a pH of around 9, you'll start to see this pink color. And then after about a pH of 10, it'll turn completely pink. So when you add it to the solution, it can't tell you what the pH is exactly, but it can tell you whether it's above or below a pH of approximately 9. So mathematically, we can actually determine the concentration of both hydrogen and hydroxide in a solution by the pH. Okay, and so the pH scale is a logarithmic scale. It's similar to the Richter scale, and what that means is that a pH of 0 is 10 times more concentrated than a pH of 1. Okay, this isn't necessarily a linear scale. It's a scale that shows the order of magnitude. Okay, so a pH of 0 has a hydrogen ion concentration of about 1 molar. Okay, 1 molar solution, whereas a pH of 1 has a 0.1 molar solution, and a pH of 2 has a 0.01 molar solution. So the pH really just tells us where the decimal place is in our scale, which is why the pH of 14 slides the decimal place over 14 times, and it has a very, very low concentration. And the opposite is true for hydroxide. We see this kind of balance here, where a pH of 14 means your hydroxide is at about a 1 molar concentration. Okay? Whereas towards a pH of 0, where hydrogen is 1 molar concentration, 10 to the minus 14 molar is what our hydroxide concentration is. So we see this sort of balance here, where the more hydrogen or hydronium you have, the less hydroxide you're going to have. There's a trade-off there. And that's because the hydrogen and the hydroxide, if you have a lot of excess hydrogen, it'll react with the hydroxide to form H2O, or water. Okay, so it'll take some of that hydroxide out of the solution. Or if you add a lot of hydroxide, your hydrogen is going to react and turn into water with the hydroxide, and you're going to wind up with H2O, which means less hydrogen or hydronium in solution. Now, mathematically, to figure this out, we can figure out both the concentration from the pH and the pH from the concentration using log functions. Okay, now this is not meant to be something that's really complex and scary. It's actually pretty straightforward and simple, and all that you have to do is punch two things into your calculator. So let's say we have a 0.8 molar solution of hydrochloric acid. We know it's an acid because it has the hydrogen in front. It's a hydrogen donor, just like in the Bronsted-Lowry definition, and it will also increase the amount of hydrogen in your solution. So in order to calculate this, we can use the formula of, to find the pH. We can say that the pH is equal to the negative log of the concentration of hydronium, or hydrogen ions. Okay, now that sounds really kind of intense and scary, but all that means is that it's just simply the negative log of whatever concentration of acid you have. In this case, it's a 0.8 molar solution. So you just take 0.8, punch a log on your calculator, and then flip the sign so that negative becomes positive, and your pH in this case would be 0.1. And we can reverse this process by doing the mathematically opposite. Okay, by definition, the opposite or the inverse of log is 10 to the whatever power. Okay, so if we say have a solution with a pH of 9, we can figure out what the concentration of that solution is. Okay, simply by saying that the concentration of your acid or hydronium or hydrogen ions, depending on how you think about it, is equal to 10 raised to the minus pH power. Okay, so what that means is that your concentration is just simply, if you have a pH of 9, is 10 to the minus 9 molar. And for all intents and purposes, we can leave it like that. Now you could write in all the zeros. There would be 8 zeros and then 1 at the end here if that's really how you want to do it. But 10 to the minus 9 is scientific notation, and that's totally acceptable. Okay. Now there's also this relationship between pH and what we would call pOH. pOH works exactly the same way, and the formulas are all exactly the same, except that the pOH looks at the hydroxide concentration. So to go from pOH to hydroxide, you would say that it's equal to 10 to the minus pOH. Okay? And so we can build this sort of grid, this chart, where we relate hydrogen concentration, pH, pOH, and hydroxide concentration, because there is this constant exchange or balance between hydrogen and hydroxide. And in fact, if you multiply the hydrogen concentration and the hydroxide concentration, you will always get the same number, and that is 10 to the minus 14th. So we can convert between one concentration to the other by dividing the concentration under 10 to the minus 14th. Okay? Similarly, the pH and the pOH of a solution will always add up to be 14. And mathematically, you can try this if you'd like, but this diagram is the big key and is critical to understanding how to solve between pH and hydrogen concentration and hydroxides. So this would be a good thing to pause the video on and to write down somewhere in your notes or on the back of your periodic table. And so to convert in between these things, the hydrogens, say you want to go, you're given the hydrogen concentration, the concentration of an acid, and you want to know the pH, all you have to do is simply follow the arrows. You start here, you're going to take negative log of whatever your concentration was, and there's your pH. But let's say instead you wanted to go from your concentration to the pOH. Notice there's no arrow directly linking those things. You have to first go through pH or hydroxide concentration, whichever formula you find easier. Now, let's say you have a solution and you don't know what the concentration of that solution is. Let's say you don't know what the molarity of that solution is. And while you could use pH indicators to figure it out, let's say you wanted to find and measure the concentration directly. There is a technique for that, and it's called titration. Now, titration works on the principle of if you have, let's say you have an acid and you don't know what the concentration of that acid is, you can take a known volume of this acid and you can drop in a certain amount of the base of a known concentration. And what you can do is you can form a neutralization reaction using a pH indicator. Okay, and so you can drop in some base into this solution until you wind up with the pH indicator tells you that your pH is neutral. Okay, when your pH is neutral, you know that the concentration of the hydrogen is equal to the concentration of the hydroxide, so the concentration of your acid and your base are the same, or the amount of moles of acid and base that you have in there are the same. So we can use this formula, MAVA equals MBVB, where the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. So, for example, when titrating 50 milliliters of an hydrochloric acid solution of unknown concentration, you don't know the concentration of that solution, but you do know you have 50 milliliters of it. You drop in a certain amount of base, and once it becomes neutral, you measure that based on the change in the level in this, what we would call a burette, that used 22 milliliters of 0.1 molar sodium hydroxide to reach a neutral pH. So what was the initial concentration? We take the 50 milliliters times the molarity of the acid, which is what we're trying to measure, equals 0.1 molar, the concentration of the base, times the volume of the base that you used, and simply solving for the concentration of the acid, you wind up with 0.044 molar solution.